In this video, we want to overview GPS data processing software architecture in geological data processing domain for the resource mining. And we are covering software architecture, process modeling, requirements verification, and network deployment. We will overview alternative architectures based on the different years and different software in those years introduced, and also we'll update the allocated steps based on the different architectures in different years, and ensure that allocation is covered in both architectures for all the required functions of the system, and we'll do analysis that key characteristics are satisfied based on the requirements as the duration of the process, which could be improved year by year. The last piece is network deployment. We will have 3 networks: cloud, on-premises, and secure, and we will allocate the software for the nodes in those networks, and we'll calculate the network mean time between failures based on the nodes used in the network reliability. So the data is publicly available for this sample. It is from the US Geological Survey and analysis. And for example, here we see those different architectures by year. 2019, 2009, 2008 architecture of the applications for the GPS data analysis and mapping. There are more information available in the provided link. Now let's go back to the model, and here in the block diagram we first of all identify those different architectures. Different architectures include the different software, 2008, 2009, and here we created as a sample 2019, which is not modeled here. Then in internal block diagram we specify actually what is that connectivity in that architecture. So pretty much following the diagram provided by the source. In 2008 we have this processing software for the US Geological Survey data, and then we have this software used, and then this one is used here with the functions allocated. Now in 2009 we see there is difference. Those are for example, for the differential global positioning system data, MATLAB is used to analyze the data, and here we see that we are skipping some step here and providing additional step in this software package, which was not previously provided by this software package. Now here we see the behavior, which was modeled in activity diagram. So we see that from the beginning to the end, we have the here process, how the GPS data is analyzed, and we have dedicated times, allocated times, minimum and maximum. Here we see that minimum and maximum allocated times. So this is 2008, and because of the modeling in swim lanes, so we have already automatically allocating those to the those functions to the architecture. So here we have 2009, so we see MATLAB is used, and here 2009 software is used, and here this additional step is here. In previously 2008 we had no step here, so it was introduced. Now here we see that full allocation. So we see here 2008 software packages, 2009 software packages, and in general software packages used across both architectures. And we see the allocations based functional allocation based on the years. We can see that all functions are allocated, and we can see that some of them are allocated twice. So it means that some of them are not used in the between one another in one another year architecture. So we need to be careful that it will not drop some functionality which is needed. So here we see this allocation, and we can also check the structure of the each year activity decomposition, functional decomposition, as deep as it goes in this decomposition tree. And I can go back. Now, next step, what we are going to do is requirements verification. So we capture requirements. Those requirements leads us to key characteristics which system should satisfy. And here in our case, we need in 2008, I will move it up. In 2008, we need that GPS data would be available in 1 day processed, and that leads to system requirement, which is 20 hours of the processing. And you see that because of the natural language analysis built in, we are extracting that shall be less than, converting directly to the constraint, so we can formalize this requirement just by typing. So for example, if I will type here shall be less than 25, constraint is extracted immediately less than 25, shall be less than shall be 25, and we can see that constraint is different. It's equal 25. So it's kind of a lot of patterns available and saves time on a requirements analysis. We can just use text. And here we see in 2009, we have 18. So we have different constraint automatically available. Now we are going to identify that actually key characteristic of the architecture in 2008 and 2009 shall satisfy different requirements. So here we see this 2008 requirement, system requirement satisfied by these key characteristics, and we can apply the key characteristic indicator as a stereotype as its measurements of effectiveness of the system. Same here, I can apply this MOE. So this is system engineering terminology, identify that key characteristic here. So this one in 2009, we should satisfy 18 hours of the processing time. And here it was 25. Let's leave it 20 in order to be more precise here what we planned at the beginning. Now here we can run the analysis, and pretty much we execute this behavior scenarios, and based on the duration of each step, we can calculate what is with the timestamp, what was the processing time in the minimum, maximum, average or random scenario. So let's do this. Let's run, for example, 2008 duration average. And here using the simulation capability of the model, which is executable, as you can see, process and whole structure. We can see here all the parts here, so we can execute, and we go through this process step by step. And here we see that we are tracking how long it took actually to run it, because we are using random. So every time we can have different times, but we can see here which process took how many hours. And in total it was 19, and we see green color, and we see that requirements is satisfied. So 20 hours is more than 19, so everything is okay. So now we stop this execution here. And here we can save this data to the file if we want. We can make the screenshot if we want also. We can just close for now. And now I can come back and see here in this, we see that with timestamp that we executed, and we got the 19 seconds, right? 19, it's actually seconds. So we see here that there was a mistake in the units. It should be 19 hours. So we will need to update this. Now we can actually come back and update this unit. So come back here. So here we see process duration, time in seconds. Let's click here and say that now it's kind of time, but it's not seconds, but it's in hours. So let's search through the units database, and we don't see any hours. Let's kind of search. Let's see what kind of time units we have. Time, seconds. Nothing very helpful. So let's create new unit. So let's say that, okay, now I want this new unit. So let's create a value type, time, and let's create new unit. Now let's specify unit name, hour, and let's specify symbol of the unit, H. let's go to the value type and assign the unit as a go here, assign the unit as a unit of this value type. Now we are going to use this as new unit here. Same here, I want to use it as a unit here, so let's use it here, so both. Now let's go back to our analysis. So we just created custom value type, and here we see in the analysis I have already hours. So that was the goal here, to fix the issue that the ISO library which provides the units, we were not able to find this unit. I think it's hidden somewhere, so we will be able to find it later. But meantime, we created the custom unit, which was applied on the property as key characteristics. So now we see that it was 19, and we can run different analysis. We can run, for example, 2009 maximum time, right? So what will be that? So let's run it. And now we go through 2009 architecture. Functional process of based on this architecture, and we execute, and you see that we are using this new components, 2009 year components. And end of the process, and we see that in maximum time case it will fail, and 18.5 hours it took to execute, right? So now we can run the same with the 2008. And if we will run a maximum case, I think it will also fail. So here we see this, it failed, and we see this is immediately red, and we see that 2009 requirement GPS data processing shall be in 18 hours is not satisfied. So we see this result. If we will run 2008 also, I think it will fail in the maximum case. So we can do this, but I'm almost sure, because this kind of coincidence on every step, that it kind of take a lot time. And here we see those kind of options in the process, where we can take from 1 to 5 hours. So if we will take everywhere the maximum, like here 3 hours, 5 hours, it will definitely be the failure. Also, we don't see here any alternative paths, but we can actually also have some kind of comeback processes based on the probabilities, in case something was not available to perform immediately, in case we need to repeat the process, and also can have the probability of those events with, for example, 0.5% probability that something is not working at the beginning, and we need to get in again data, and so those kind of probabilities are easy to introduce here. I can even specify here, for example, that we have here a probability that this path will be selected 0.95% or 99%, and 1% could be that we need to come back and reevaluate here. So let's say that I have the merge, and this merge will start here. I can move it here, the flow, and I will be able to say that at that moment, actually it's not very convenient here, but I can say that in this case, after this step, maybe I will skip those 2 steps, and I don't need those 2 steps. In the rare case, I can just go here and merge to this place. Let's move it here. Merge the flow, and we have here alternative path, which is very rare case, so probability 0.01, so 1%, so 99% that we will go to do the graph nav processing software, and this processing software US geological data processing software, but now in the 1% probability we overcome here. So we know that we can execute this, and it was actually 2008, and we can run it in maximum case, and still we will not be sure that we are sure that it will take the maximum time, but we are not sure that how that happens, that it will take this path which is actually avoiding those two steps, it will save time, right? But how often that, right? So we have this uncertainty quite a lot in the processes. Could be more uncertainties related to also hardware and not only software what we have here work. And we see here that this requirement failed to 22.5 in our case. Now let's go back here and let's see that actually in results we recorded automatically that with that timestamp we have this failure here. So 2008, I can sort by name, and here we see 2008 and 2009 execution. So here this timestamp failed and this requirement of 2008 failed. Now, but how to know that the probability of the likelihood of failure? So for that, we can run many times, like 1,000 times, using Monte Carlo analysis, and the industry standard is to run thousands of times, 10,000s of times, and get results, and then see what is the likelihood of failure of this process when we run most required number of times, which is provided by the industry best practices. So now I will do this. I will run the 2008, and here we see those configurations of execution. We input the what kind of output of the visualization is needed, but there is no coding here, just model, and we see this just like configuration of the execution. So here we are running 2008, and we see the output of the results, and we see that here we see on this process duration property the X, and we see that number of times it was in that range as a red bar. So we have from 19 to 19, from 80 to 90, we see here, right? So this bar. And then from 90 to 20 is this bar. So this is the most likely one. So it's kind of normal distribution. Bell form distribution. This is what is expected. And here on the Y, we see here number of runs which fell into this category. So here we see in this category between 8 and 19 seconds, it was 34 times. And this dynamically updating, we have for now 235 times executed. We don't need simulation visual representation because we just run as fast as we can this process. And will take some time to finish. And we see here there is also analysis data available in the corner. So we see here that number of times 300, mean is 19, standard deviation is 1.42, and out of spec is 0.4. So 40% of the cases failed. So that's failed based on the requirements not satisfied, of this property not satisfying those requirements. So we see kind of probability that based on this process, we will satisfy requirement. So this is in 1,000 runs case. So we can wait, and at the end, we will get the final result. And here we can export data to CSV. We can at any moment stop if we see something is wrong with execution, and so on. So let's stop for now. We see here that half cases executed. If this would be analysis which we want to have, we would run a required number of times. Now I will close this. So here we see frequency, here is process duration. And I will not run 2009 for the long time. I will just execute shortly to see that it actually has different kind of out of spec case. You see here it is for now it is lower, so we can expect that it will be lower also at the end, but now it's kind of increased. So let's see. Yeah, so it's a bit lower, right? Okay, so let's stop it for now. Now the last step is the network deployment. So here, once we have the software, we can actually model network structure, and we did that here. And here we have network structure 2009. We have cloud-based network, on-premises network, secure on premises, we can have additional networks, and based on that, we deploy the servers and clients and other nodes required by this total network. So here in 2009, we have this deployment topology. Here we see here cloud deployment architecture. We have on premises, we have secure on premises, we have ports between. Those ports can be used to specify what protocol we use to communicate, what data we get through, what port number is here. So we can specify the number of port which needs to be open. So this can be used to specify and show that for the someone working in the network to know where they connect to. Here we see also legend applied. So we have the software which should be purple. So we know that legend item is not applied. So we can select those components, software components, right click and go to the legend and choose this as a software. And we will get applied the style based on the legend. Same was done for the network and same was done for the nodes. Now, if we would want to take something from the software components and say that, okay, we want some new software applied, like for example, client, here I can also have MATLAB to do analysis. In 2009, I can take this MATLAB component and drop it here. So I have MATLAB now as an additional component here. I can expand and specify that it is also deployed here. I can apply the legend. Right click, legend item, software, apply. So based on that information, so this is just for knowledge, right? It's kind of quickly way to specify this deployment architecture. Also, the way could be to use this as for analysis. So we can, for example, analyze, specify the based on different servers used, like application server can have mean time between failures, database server client can specify that, and calculate the total network reliability. So I can take this network in this diagram, for example, I can run here and calculate the total network reliability. So here we see that's done based on parametric diagram, which is completely transparent. And we can calculate all different characteristics. For example, maybe we have in parallel servers, maybe we have in a series, and we might need that some processes will never stop. Some processes could have some failures when the network fails. So we can allocate those software to right network servers. Can be done without any problems based on the process analysis which we did and also the network topology which we modeled. So here we have this model and it is actually covering some specific component, software component for the GPS data processing, and it could be incorporated in bigger picture system of systems, and also could be as a result of requirements following the magic grid method and framework, which can start from the stakeholder needs, go to the use cases, and as a result, this component will be introduced in based on different use cases, different user requirements, which we just touched a little bit, but here we will have this component in different years, different evolvement of this component architecture based on the whole system as organization solution for the software applications, but also hardware. So thank you.